Hello, ECE Badger alumni. We're thrilled you're here. And as we're having people come in through the waiting room, I am going to encourage you to go to the Zoom chat and let us know where you're joining from and in what year you received your ECE degree from UW-Madison. So again, welcome. We'll give folks just another minute to get in from the waiting room, and then we'll get started. We're delighted you're here. And again, let us know in the chat in Zoom where you're from and what year you received your ECE degree. Hello, Sue Guzman from Santa Clara, California. Great to have you here. Everyone else, we want you to jump into the Zoom chat and let us know where you're joining from and what year did you receive your degree. We have somebody all the way from Verona, Wisconsin, and Fitchburg. So far, California is winning the distance game here. And I think we've just got, it looks like we've got 3 more folks in the waiting room. If we can get them in, then we'll get started. All right. Welcome, everyone. I am so delighted that you're joining us today. My name is Susan Hagness, and I serve as the Department Chair of Electrical and Computer Engineering here. I want to kick off this summer ECE virtual town hall by first, again, welcoming you, letting you know how grateful we are that you're joining us today, and encouraging you to follow us on LinkedIn. We have a very active social media presence on LinkedIn with our UW-Madison Department of Electrical and Computer Engineering account, and you can get all kinds of great updates, and you can also help us increase our visibility by engaging with us in that way. There's also a QR code on this slide, and I want to encourage you all to take a photo of that and follow the link. We've got a pretty quick Google form that you can fill out to let us know how you'd like to engage with us as one of our alumni if you aren't already actively involved as an alum in the life of the department. It looks like we've got some great locations coming in. We've got California and Florida. It looks like that's the farthest distance so far that I see on our list. And if you haven't yet added your location in the Zoom chat and your degree date, please jump in there and let us know a little bit about who you are. So I'm going to go ahead and kick things off here. Today's town hall focus is on AI, but before we dive in on that specific educational and research topic, I want to give you a quick overview of our department at large. So the ECE department at UW-Madison now has experienced a significant period of growth. Actually, I'd say phenomenal growth. We've got an outstanding faculty that span 8 core research areas, and these areas are highly interdisciplinary, as you can see from all the connections our faculty have across these 8 core research areas. Now, autonomous systems and intelligence has been one of our strategic hiring areas and themes. And we've been really fortunate. Over the last 7 years that I've been serving as department chair, we've brought in actually 27 faculty total, and about a dozen of those are new faculty who have expertise in the foundations of AI, foundations of artificial intelligence, and the related field of optimization, as well as computing systems that power AI. And so it's my great joy to introduce you all to our 3 panelists today. We have 3 ECE faculty at various career stages. I want to welcome Ramya Vinayak, who is one of our stellar assistant professors in ECE. TW Huang, his full name is Tsung-Wei, but he goes by TW. TW is one of our brand new, newly tenured associate professors in ECE. And then we have Rob Nowak, who himself is an alum of our department and also one of our very senior faculty in the area of AI. So I'm going to ask each of them to take a moment to introduce themselves. Give our alumni a 1-minute description of the kind of research you do, the types of courses you teach here at UW-Madison, and then we'll dive in on some questions. So Ramya, why don't you kick things off with introducing yourself?
Thank you, Susan. Hi, everyone. I'm really excited to be here with you all in the town hall. Looking forward to the interaction today. My research broadly is in the area of foundations of machine learning algorithms that power the AI systems. And the work that is ongoing in my lab focuses on addressing the challenges that arise when we want to deploy AI systems in a safe and reliable way. This includes understanding and addressing challenges related to how do we incorporate human feedback in a meaningful way? How do we elicit and learn human preferences and values so that we can align the AI systems to the goals that we have? How do we collect good quality data in an efficient way? And we use both mathematical foundations, like tools to look at like fundamental questions related to these topics, as well as scientifically grounded empirical approaches to solving these problems. And in terms of teaching, at graduate level, I teach courses related to mathematical foundations of machine learning, and also some of the um, fundamental mathematical tools that goes into it, like linear algebra and probability. Also at undergraduate level, like probability and random processes. And looking forward to interacting more. And I'll hand off to TW.
Sure. Hi, everybody. I am Tsung-Wei Huang. Most people just call me TW, a lot easier to remember. So my research has been focusing on the intersection between circuit design automation and high-performance computing. And essentially, we are building software to help people more efficiently use modern computing hardware like many core CPUs, TPU, GPU, and clusters, and so on and so forth. For example, we are building open source software, like makes it much easier for people to program and scale your application across different processing unit with application in areas such as artificial intelligence, AI, design automation. We write software to help you more easily and quickly design integrated circuit and even more quantum computing. So I especially like collaborating with the people in industry because I believe we can learn from each other and solve important problems together that matters to the industry. And for example, over the past few years, we have been open sourcing our software tool that have been used by many people in both industry and academia. Here at UW-Madison, I'm teaching a course like EC 759. It's a high-performance computing course. And students in this course will learn how to program parallel computing resources, like many core CPU, GPU. I'm also teaching computer ADA design. And the student will learn how to use software design algorithm to develop a circuit that is essential for today's electronic product, such as computers, smartphone, VLSI, and so on and so forth. So I'll be happy to have more interaction with everybody in a later panel session.
Great. And hi, I'm Rob Nowak. I work on the theoretical foundations of artificial intelligence, basically trying to develop new mathematical frameworks that will inform the better engineering design of these systems. And I can say more about that as we go. I teach a variety of courses at the undergraduate and graduate level in the areas of machine learning, artificial intelligence, and signal processing.
Great, thanks, Rob and Ramya and TW. So I'm going to pose a couple of initial questions to our panelists, and then we'll transition to a Q&A with our alumni, with you all. We have a number of alumni who submitted questions at the time of registration for this town hall, and I've got those queued up. We'll have our panelists provide their thoughts on some of those questions, but we'll also open things up to questions submitted in real time here in the chat. So let me start with our first question for all three panelists. Let's hear from you all. on what you see as the most promising foundational ECE research directions in AI today. Rob, you want to start, and we'll
Sure.
then move to TW and
Yeah.
Ramya?
Yeah, well, maybe I just start by saying that I think everybody's familiar with the kind of state-of-the-art AI systems like OpenAI's GPT, Gemini from Google, X's Grok. These are some of the most complex engineered systems that exist today. And they involve a lot of different components, but two of the main components are the system architecture. These are typically feed-forward neural networks with nonlinear layers and adjustable weights. I imagine many of you are sort of familiar with the basic idea of a neural network. That's what these systems are at their heart. The other key ingredient, and I'm thinking mainly about kind of the software side of things, TW probably could tell us more about hardware side, but on the software side, the other main thing are the training algorithms. And these are the methods that adjust the weights so the systems correctly map inputs to the desired outputs. That's what training means. And so obviously there's been a ton of amazing progress, but there are some really big challenges. And these are challenges that I hear of from the leading teams at OpenAI and Gemini and Anthropic and the others. And one is called the scalability gap. And this means that what's typically done is we try to improve the architectures or improve the algorithms that are used to train these systems and to test out whether these proposed things really will improve the systems. They first develop the ideas on small scale prototypes. These are still very large engineering systems, but they're nowhere near the full-blown Gemini, for example. And what happens though is they might see, oh, this new idea for the architecture really seems to improve on these small scale models. But then when we field it and put it into the real full-blown Gemini system, we don't see any improvements, or maybe it even hurts the system. And so it's very, very hard to predict what changes to make to the algorithms and architectures to actually continually improve these systems. And frankly, there's really very little understanding of how to do this well. So what that means is a lot of the process of engineering these systems is trial and error. We're designing architectures and algorithms using a mix of art and science, and a lot of art, right? And so what I think is a real opportunity for ECE and the whole AI community more broadly, but particularly in the academic realm, is to try to move us towards making AI design more principled and predictable. And so in my own work, this is, I'm targeting just, can we understand at a deeper level how deep neural networks work, and how they generalize to new data once they're fielded. And this work really draws on theoretical foundations from tools that are pretty familiar in ECE. For example, signal processing, optimization and control, and then the associated areas of mathematics like functional analysis, stochastic processes, and probability theory. And maybe I'll just kind of wrap up with an analogy that I think kind of captures where we are today. I think modern AI systems, the ones we're using now, are like Roman bridges. They're impressive and functional, but largely built on intuition and tradition. And it really wasn't until the 18th century that we actually developed the scientific principles and processes for designing really good bridges. And so it took, again, centuries, right? We had bridges for a millennia before people really understood the science behind it. I hope we can do better with AI. I hope it won't take centuries. But really, we don't have that full, comprehensive scientific understanding of these systems that would enable principled engineering. And that's what we're working towards. So I'll pass the baton if that sounds good, Susan.
Yeah, sounds great. So Ramya or TW, either one of you want to add to that? What do you see as the most promising foundational ECE research directions in AI today? And I'm going to stop sharing so that we can see our panelists a little bit more up close here.
Yeah,
Right.
I think I can add to what Rob was talking about, like with respect to the architecture, optimization, and I want to add another piece that goes into this making AI systems successful is the data that goes into like training them, adapting them to specific domains, to be able to align them to the goals and preferences that we have, because we want to be able to deploy these systems in a way that is safe, reliable, auditable and controllable. Right. So I think engineering principles play a very key role in also looking at the questions from the perspective of like, how should we be building these systems so that they are safe, reliable, auditable, and controllable. And towards these goals, I think including like the research that is ongoing in my lab as well as the MLOps group here in ECE department, using like mathematical foundations can be a very powerful way to look at some of the fundamental questions, like what aspects are like possible, like what are some information theoretically like possible things to do, and what things like seem nice but are not achievable in the way we are looking at them. And I had a different analogy, like I liked that Rob gave the bridge analogy. So the analogy that comes to my mind is steam engines, right? Like, so when we had steam engines kind of before we really understood thermodynamics really well. And so there was a period of time where we thought perpetual energy machines are possible, right? It took us a while to understand like, hey, no, energy can be transformed from one form to another. So, I think we are kind of like in that era of like, we have lots of these really cool, interesting, technologies that are available to us, but we are still at a place to really understand what are the limitations of these, what things are possible, what things are not possible. And I think ECE domains, signal processing, information theory, and what we consider systems in ECE, it's the background that I come from, I think really provides a great way to approach these like foundational fundamental questions, as well as that enables us to build novel, practical, and safe algorithms and systems so that we can have great technologies that kind of coexist with us, help us, and kind of create a future that we envision together. And I think the other aspect that is hardware, I guess, like, a TW will be able to give us a much better perspective to that. So I will pass the baton on to TW.
Thank you, Ramya and Rob, for giving the valuable comments on this. And as a faculty in computer system area, I definitely see a lot of promise and opportunity in the intersection or convergence of AI and system level optimization, especially in rethinking how we can build a more scalable and energy efficient computing infrastructure to support AI in not just training, but also the inference. There's a large language model training is very, very, very compute intensive and energy, consume a lot of energies. And in computer system area, we have a lot of faculty working a lot on the foundational directions, such as how we can build a more efficient hardware to support today's machine learning workload, efficient algorithm hardware co-design, where the machine learning models can be developed together with a hardware constraint in mind. Right? Because today, people, when you are designing a machine learning model, most of the time you do not actually look into the hardware constraint. So there's a lot of opportunity and also the gap that we have to solve when it comes to hardware and software co-design, so we can design a more energy efficient and scalable AI model. In the other direction, we are also exploring is the distributed or parallel computing method, a more efficient parallel computing method to make AI more approachable, especially in reducing the training and inference costs of today's large language model. Energy efficient computing is definitely one of the biggest direction. We have a lot of people in the CAS, computer system architecture area, driving innovation in circuit architecture, scheduling, runtime, and so on and so forth, trying to make AI as energy efficient as possible. So these are just some example of foundational effort that EC faculty are looking into. Because AI for us is not just about building a smarter model, a bigger model. It's more about how we can compute those models fast and more efficiently.
Thanks, TW. TW, I'm going to go back to you with this next question, have you start us off. Share with us how your research groups are involving undergraduate and graduate students in AI research.
Sure. So in my research group, we focus on building a lot of software system. Like I said, one of our research focus is we want to simplify the development of performance critical application. And AI machine learning training inference is one of the key focus in our research. And so I train students, both undergraduate and graduate students, with a lot of hands-on experience in building software system, hardware architecture, so they can learn how to program those emerging computing resources, CPU, GPU, TPU, or some other new accelerator to make today's AI programming a lot easier to handle. So students in our lab can often gain a lot of hands-on experience, not just system engineering, programming, but also the real experience in building chip and hardware. And a lot of time, this experience can turn to open source software that student can open source their innovation, see some impact in the long run, and people from both academia, industry, outside EC can get a taste on open source software where the student can see the impact, whether they want to use the system to accelerate AI or leverage AI to improve the system and so on and so forth. So those are the primary focus I've been working in my research lab, and also train students with hands-on experience in both software and hardware.
Great, thanks, TW. Rob, you want to share your experience with training, getting undergraduate and graduate students involved in AI research?
Sure, yeah. So, I have students that involved with my group at all levels, undergraduate, sometimes even some high school students, all the way through PhD students and postdocs. And they're also involved in AI from really foundational theoretical work to developing and prototyping systems for real world applications. So I'll just describe a little bit about that. In the PhD student and postdoc realm, some of the topics that they're looking at would be, for example, like I described earlier, studying what kinds of mathematical functions are actually learned and represented by deep neural networks. We train these systems. What exactly, they take inputs and they produce outputs. So they're a system. What kind of system is that? How can we characterize that? That's one line of work. We're also developing theory and tools to analyze capabilities and limitations of these models. And then also using AI in some applications, for example, AI to improve imaging systems, both in the realm of medical imaging and reconstruction, and also satellite-based atmospheric imaging. Some other projects aim to improve the efficiency of training. I talked about how one of the bottlenecks is really figuring out what changes to make to algorithms and architectures, and then how to explore that whole design and engineering space more efficiently. So that's one thing we're doing. That translates into something I think I saw in the chat was just about how to make these systems less energy intensive. So that's a big component of our work is trying to figure out how to do this with less intense computing. And then we're also, and I think Ramya will talk a little bit more about this, so I won't say too much, but we're looking at designing AI systems that are better aligned with user preferences. And one of the focuses of our work there is trying to develop methods to make AI systems like chatbots have a better sense of humor. And one of the ways we've done that is over about a decade, I collaborated with the New Yorker magazine on their cartoon caption contest. And through that collaboration, we gathered what is now the largest online data set of human judgments about humor. And we can use those human judgments about humor, these are cartoons and cartoon captions and jokes, we can use that data to help fine-tune these very large language models so that they're more attuned to the kind of preferences and style of humor, particularly in the context of this cartoon caption contest. So that's been a really interesting project that connects with art, but also AI and cognitive science and psychology. And yeah, so that's something fun. On the undergraduate level, we have had, many of them actively participating in various aspects of all these projects. A lot of them have actually gone on and co-authored papers in recent years, and then they typically go off and go to graduate school or industry somewhere else. And so that's been great, and it's really fun to try to involve them and see them develop as researchers. So I'll pass it over to Ramya.
Thanks, Rob. So I think I'll start with like the preference learning aspect, like we hear a lot about like aligning AI to human values or human preferences, but it's actually not such an easy thing to elicit human preferences. How do we elicit human preferences, and how do we learn preferences that are heterogeneous? Because not everybody is going to have the same preferences or even same like values and goals. So I work on mathematically modeling. As well as like building novel algorithms for learning preferences, especially heterogeneous preferences. And it's been a great space to also collaborate with psychology, and Rob and I have a collaboration with a psychologist on campus, and it's been a great way to kind of have um, uh, like immediate applications that kind of like is very fun to kind of like build off many of these ideas, and to see some of these very mathematically grounded ideas translate into interesting results in cognitive and behavioral sciences. And more recently, I have also been, building collaborations with researchers in survey sciences, in polling, in opinion collection, like. So the areas where people have been for decades investing time in collecting human, preferences, and how AI can help them, and how the research in those areas can help us building these kind of algorithms and models for learning preferences in AI. And the other line of work, where we are looking at efficient data collection with guaranteed reliability, human in the loop AI systems. All of these actually involve both mathematical modeling, looking at algorithms, mathematical analysis, but also we focus on implementing these algorithms, running experiments on real data, like building open source software that we can really use as well. So, and students can get involved in various levels. So I work with students, some of them graduate students who are mostly focused and interested in the mathematical and theoretical aspects. I have graduate students who have been very keen on applied engineering questions. And I have also been really had enjoyed working with undergraduate students. I have undergraduate students kind of involved in different levels. Some students, it depends on like the bandwidth and the interest of the students. Some of them want to come, maybe have like a little toy project and just get a flavor of what does like doing research feel like or look like. Some students are really keen on maybe spending like a summer or an entire semester doing, or like 2 semesters, or doing a senior thesis. And those students get involved a little bit more in the longer research projects and have been part of publications. I have had, 2 students who have gone on to do masters in different universities, like undergraduate students who worked in my lab, now in UPenn. Another is going to UMesh. I had one of the grad students in my lab was an undergraduate student at UW-Madison who got so excited about research experience that he continued to do masters and PhD here. And I also want to point out that some of the courses that we teach, like ECE 331, which is probability and random processes, ECE 524, which is introduction to optimization, ECE 532, which is linear algebra. All of these are like the pillars that go into machine learning, which fuels AI systems. And I think that helps in also preparing undergraduate students be ready to gain these experiences in research labs.
Ramya, that's a great segue into my next question. So I'll start with you. What types of career paths are you preparing your research mentees for?
Yeah, actually, yeah, this is a really good question because the career paths, in one way, it depends really on the individually what students are motivated in, but also like what opportunities are available, right? And the landscape of what opportunities are available is changing very fast, and I envision it will keep changing faster and in you know unpredictable ways potentially, but it will involve AI and the workhorse that goes behind AI, right? So and I think that's place where, like, I think as I was mentioning, like some of the foundational aspects that go into machine learning and AI helps students to kind of get these basic tools so that they can apply it to the questions they're applying it to right now, but also can translate it into a different domain or a different question and adapt themselves as they go. And the other aspect is also, I think, in the research, when we are like looking at like the whole system and looking at all different parts, like I make sure that my students who are doing theory also are involved in discussions about experiments and they understand like how some of these systems are built. I strongly encourage my students working on theoretical aspects to also do some level of hands-on experimentation, not just in terms of like getting experience and skill in coding, but also I think sometimes even fundamental questions for me, it's when you get your hands dirty and see how things work, it's very great way to kind of look at go back to the whiteboard and write new questions and start like from scratch. So that is actually also helpful for their research, but it's also preparing them for potentially other types of career paths if they need to kind of switch. And on the other hand, like students who are focused mainly on empirical questions and applied questions, they have also been gaining a lot from understanding the foundational aspects. So I look at this as like, we learn math, but not necessarily for doing research in like math, but we use math all the time. And like every area in ECE, we use mathematics in different ways. So I kind of look at it that way, that even students working on empirical questions, they're also very well prepared in terms of foundationally, so that even though maybe the specific type of software engineering position or something, it gets changed, that landscape changes, but they have such strong foundations that they can switch to using different tools and do the tasks that they want to do. And the last thing I want to point out is that we strongly encourage our students to also gain experience through internships. I have 2 students doing internships this summer. I think that's a great way for students to kind of look at what goes on in industry, like what kind of career paths that they could envision there. And the other thing is actually machine learning conferences attend, because it's widely attended not just by academics but a lot of industry presence. I would say more than half of the attendees at NeurIPS, ICML, ICLR, these conferences are from industry, and that has been a great help for students to build the networks and connections to look at different career paths.
Thanks, Ramya. Rob, what about you? What kind of career paths are you preparing your research mentees for? Where are they landing?
Well, pretty much all that you could think of, industry, research and engineering, academic faculty positions, and also government labs and agencies. I have students who've gone on in all those different tracks. For example, in government agencies, I have a current student who's actually a member of the Air Force Research Labs, a former student who's also there. So they kind of go all over, and the preparation is largely the same. And I would say the main kind of skills and so forth that I hope students develop are one, an ability to identify and abstract key engineering problems into mathematical terms. That's basically how we reason, right? We need to take a real world problem and map it into something we can study mathematically. We can also run experiments, right? But I think there's no substitute for good mathematical models that at least provide some insight and guidance. We're not just shooting in the dark. They also need to have the capacity to work independently, but also lead research efforts with others. And that gets into also trying to get all of my students involved in some level of team collaboration, and then also mentorship of more junior students along the way. And then finally, wherever they're going to go, they're going to need to have strong communication skills. And in our business, that means an ability to explain complex ideas clearly, both to experts, but also general audiences. So they need to be able to have that ability to get into the weeds if they're talking to experts, but also bring it up to a higher level if they're trying to communicate to people who aren't quite as knowledgeable in the subject area. So those are the key skills. Yeah, I'll pass it over to TW.
Thank you, Rob. So, I prepare my student for career primarily on the area they can design and build high-performance system and apply those systems they build to accelerate different application. For example, student can design new GPU programming system to accelerate AI workload, quantum computing, and other scientific computing problems. Or they can try to leverage some of these AI technique to optimize the system design, such as, can we use AI to recommend a good resource utilization plan for scheduling all these different jobs in the HPC cluster. And because my work primarily span across different areas, both software and hardware, computer architecture, and student can pursue career in not just software, but also the hardware industry. For example, over the past few years, my students have been working either as a full-time or intern for companies such as NVIDIA, Intel, Cadence, Synopsys, Google, Microsoft, and so on and so forth. So these are some example of the company or industry that I train my students to pursue their career for. And on the other hand, the opportunity I found is by talking to many of these company people, very often I found the skill set to write software they can utilize high-performance software, high-performance computing resources is very, very demanding. And that is especially true in today's AI-centric industry where many applications are powered or driven by high-performance computing resources. Right? You run your AI model, then you easily spend lots of resources across thousands or even millions of processing cores. There is very, very compute intensive workload in today's industry. And for example, how computation is parallelized, how memory is managed, how performance is optimized on modern hardware. All these are very essential in understanding the software and hardware stack of today's AI system. So I often train my students in this area, and they have to know how to design the system and optimize them across different areas. And I also want to kind of like circle this idea back, following up on what Rob just mentioned. When I supervise or mentor students, I always told them, your career success, perhaps only 30% comes from your technical capability. 70% of your career success is dominated by communication. Whether you are able to communicate your idea to your manager, to the generic public, or to your peers so they can help you, you can collaborate with different people together is critically important. And lots of time is even more important than having a good technical capability. So communication is something I also emphasize a lot when I'm training the student toward their career.
Thanks, TW, and you're getting resonance here with some of our alumni who are giving you a thumbs up on ensuring that our students are graduating with really strong communication skills. Well, let me dive in on some of the questions that came in earlier from our alumni, and then we'll add into this Q&A session some of the questions that have come in here in real time in the chat. So first question from one of our alums is a question about programs that cater to AI. And I'm assuming that this is referring to degree programs or educational programs here within ECE at UW-Madison that cater to AI. And I'll start off with a high-level answer to that, and then our panelists can chime in with any further information they want to share. So very briefly, we have degree programs and degree features now in ECE at the undergraduate and graduate level that didn't exist 10 years ago, and that we've specifically evolved our educational mission to address because of the way in which AI has emerged. So at the undergraduate level now, both of our undergraduate bachelor's of science degrees, electrical engineering and computer engineering, all those students have the option of adding a named option to their bachelor's of science degree. And it's a specialization in machine learning and data science. And then at the graduate level, a degree program that didn't exist 10 years ago is a machine learning focused accelerated master's degree. Our students can get that training in 12 to 16 months, that extra credentialing. And then, of course, we have a large number of graduate students that are focused now on AI-related research in our PhD program. And you've just heard from TW and Rob and Ramya about the types of research that they're engaging students in. And of course, a lot of those are PhD students. TW and Rob and Ramya, do you have anything else you want to add to that question, or should we jump into the next one? You're welcome to add anything.
I could just add a little. I want
Yeah,
to
please.
mention that both at the undergraduate and graduate level, our courses and programs in AI and machine learning are really coordinated and cooperated on between just ECE, but then other engineering departments. ISYE is one, industrial engineering, and then a lot with computer sciences and statistics and math too. So one of the great things here, and I think as alums, you guys all know this, we're really proximate to each other. So, engineering is close to computer science and statistics is across the street with math. And I'm actually in the WID building, the Wisconsin Institute for Discovery, which is sort of in the center of it all. So we have lots of cooperation among all these different programs. We each have our individual kind of efforts, especially with undergraduate programs where they're getting a degree in X, but there's a lot of shared resources and teaching responsibilities, which make it really fun and well-rounded. And so I'm really happy that we have this situation at Madison, which doesn't exist at everywhere else. Sometimes you'll have the math department a mile or two away from engineering and computer science, which is never great. And so we're really lucky here that the core departments that are involved in AI research and teaching are very close together to each other and work really well together. So I just wanted to add that in.
Yeah, that's a great add-on, Rob. Thanks for that. There's an interesting question that came in that's very high level and broad, and I think it's on a lot of minds, and that is how to avoid becoming obsolete in the age of AI. Anyone want to tackle that one?
Yeah, I can chat on that one. So, today's AI is very fast moving, and I think the key to avoid become obsolete is we have to teach our student the importance of continuous learning, and also prepare them with a very strong foundation. I mean, very often I talk to people from not just academia, but also industry, those who are claiming they are working on AI. It's not just about import PyTorch from Python, but more importantly, they have to understand the fundamental like algorithm, system, hardware, and more importantly, the linear algebra behind the AI. Especially with a lot of this open source software tool and cloud computing platform available in the AI industry, I start to feel like this critical thinking and foundation, mathematical foundations are very, very important. And as long as you are equipped with all those foundations, you have a solid knowledge with this foundation, you won't be obsolete. Because eventually all this knowledge are the same. You can apply to multiple areas, not just AI, but also some other application. So that's my 2 cents.
Anyone else? Robert, Ramya, you want to
Yeah,
jump in?
I want to, second what TW mentioned. If I like looking back into I my undergraduate training in electrical engineering, I had no idea what even machine learning was, let alone like AI systems. And my research today focuses on AI systems and machine learning algorithms. And I do feel um, the foundations that I got, both mathematical foundations, like whether it was probability, linear algebra, optimization, and signal processing, communication, information theory, even though at that time it was wireless networks that were the hot topic, and that was the main kind of motivation for learning some of those foundations. Those fundamentals, now I can use them to tackle different sets of questions, right? I think that's something like really great about like having um, like, for example, signals, initially, like, while we motivate a lot of things from physical signals and things, we can also think of signal that comes from data that we collect from people. So once we have like those like fundamental skills, I think they're very transferable. I think that's something that I try to emphasize to both graduate and undergraduate students in particular, because I think sometimes we tend to think that, oh, we need to be learning something like completely different. What we need to be learning is like changing, like as we do in EC curriculum, we can change the courses, we can change the motivations for it, and we can incorporate something new that goes into to that. But some of the core foundations are, I think, is what helps us to not be obsolete and keep kind of learning new things, adapting to new dynamics that kind of arise. And the other aspect is, it connects back to what Rob mentioned when he was talking about preparing students for career paths, is a very important transferable skill regardless of like what one is doing. Is this the engineering gives us this way of problem solving, right? Like, so kind of whether the students want to be in engineering, or I've had like some of my undergraduate friends, even though with the same training, ended up going to be like um, um, consultants and completely different directions. And they're still, when I talk to them, the reason, like, they have been able to make those changes from the same, I guess, foundations is because, I think engineering gives us that strong foundation to be adaptable. And so I would say adaptability is how we will not be obsolete. Like, or it's important to be adaptable to not be obsolete.
Thanks, Ramya. I'm going to jump to a question from one of our alumni here on this town hall meeting. Michael Keaton asks, what is the next technology on the horizon that could reduce computational power required for AI data centers? How soon? The analogy is, what is the LED light bulb of computer processing that will reduce data center load? Would any of you like to jump in on an answer to that question?
Yeah, I think I can comment on this. I mean, if you look at today's AI deployment, the biggest challenge is definitely the energy consumption. And to just give you an example, if you run your application on just one GPU, the energy consumption is going to be 8 to 10x more than running the same thing on CPU. Lots of time, the energy consumption, the energy is eaten by moving the data. And computing data model, computing AI model itself is not very challenging. The most challenging part is to move data around, whether you are moving the data from cloud, from user, from system, from one layer to another layer. So I think the next biggest challenge will be architecture, whether people can come up with a more energy efficient architecture that can solve the data movement problem, because 90% of the energy is eaten by moving data. Computing AI itself is not very challenging, but the biggest challenge comes from moving data, and how you move data more efficiently, how you organize the data more effective across both software and hardware stack is going to be the next challenge. So I think those who can solve this will become the next superstar. And EC does have a unique advantage in addressing this challenge.
Great,
I
thanks,
hope that
TW.
answered the question.
Yeah, that's a good start. And then, Michael, I'm also going to suggest that one of us will follow up with you. Our February town hall back earlier this year had a panel that was focusing on AI data centers and how we can create more energy efficient solutions. And so we've got a recording of that, which we can get you a link to as well if you want to hear from some additional folks who are working in that area.
Can I just jump in with an
Rob,
analogy?
Please.
And I think, TW, gave great answer. I just wanted to kind of mention something else that was a kind of power hungry or constrained application, and that was deep space communications, or it still is. So when you're transmitting from Mars, say, again, you're going far away, and you have limited power on your space probe or whatever. So what happened there over the last 50 years? Well, basically, the improvements and gains we've seen in the overall efficiency of deep space communications are roughly, I would say, half related to hardware innovations, better, more efficient hardware. And then the other half was coding theory and information theory, just better ways of encoding the information so it could be reliably decoded from weak, corrupted signals. And I think that's what I would anticipate for AI energy efficiency too. It's going to be better hardware, but it's also going to be better software and algorithms. And so, across ECE, I think especially we have representation on both ends of that whole spectrum. And so it's going to take breakthroughs in both areas, not just hardware, but also probably really rethinking some of the way we implement these systems in software.
Yeah, thanks, Rob. That's great. I want to jump to a question that came in about, let me see if I can read the exact wording here. Let me find it. Give me just a second. I know where it is. Okay. It's a question about, okay, where is it? Give me just a second. Comment on whether recent changes on federal research funding have affected projects in UW-Madison ECE department. I want to give a real quick answer to that. That's a topic that we could have an entire hour-long or more conversation on. So Bob, to you and anyone else that had a question about this, yes. The recent changes in priorities with federal research funding, the threats to the level of federal research funding, it has affected the research enterprise here within ECE and across UW-Madison and across the entire nation. It's a big concern for research universities, and we anticipate ongoing concerns in that realm. So how are we adjusting? Well, it's not easy, but we are a resilient bunch, and we are seeking alternative sources of research funding. We have a pretty significant portfolio of research funding within ECE from the Department of Defense. And there's been, I would say, less of a threat right now to the DoD funding than, say, National Science Foundation, where we still don't yet know exactly how things are going to shake out with the next year's budget at NSF. You've certainly all heard in the news the ongoing threats with funding from NIH. So one key strategy is to continue to maintain a very diversified portfolio and to also expand further into industry funding. And that's where partnerships with our alumni can be incredibly valuable. And so that's a segue into another good set of questions that came in. Two of our alumni submitted questions in advance. How can alumni help support the department achieve its goals? And also, are there opportunities for alumni involvement? And I want to make sure we don't run out of time for addressing both those really good questions and welcome questions. So, the department right now, we've had some really vibrant growth, not only in terms of faculty that I illustrated at the very beginning of this town hall, but also in terms of our undergraduate and graduate student populations. So that's exciting. And we've got a bold vision to grow our impact further in research and education and elevate the department into the top 5 in both undergraduate and graduate program rankings in the US. Ways that we can grow ECE into a nationally recognized entrepreneurial hub for faculty and students. One of the questions that came in had to do with entrepreneurial activities. I do see that as an important area for us to further build. And I'll just answer really quickly a question about the department promoting entrepreneurship. You may not know that we actually have at least a dozen active startups right now that have been launched by ECE faculty and students. And our college co-founded a technology entrepreneurship office, which supports and mentors students and faculty in areas related to tech transfer. And it also serves as a gateway to the NSF I-Corps program. So we're really keenly interested in partnering with industry, not just through startups, but also working with alumni in established companies to continue to transform inventions out of UW-Madison into market-ready technologies. And then back to how alumni can help us achieve our goals. So I've got a QR code on this slide. And if you follow that, you can tell us how you'd like to engage. So there are so many opportunities for our alumni to help us, to partner with us. We welcome our alumni engaging with us as guest speakers in classes, student organization events, panels throughout the year, seminars. We engage with our alumni on our ECE advisory board that I meet with twice a year, formally here in Madison. Interestingly, AI has been a recurring agenda item at our past several meetings. Our alumni, as I mentioned, they're involved with us in entrepreneurial activities. And I would say now more than ever, industrial partnerships and alumni philanthropy, they are critical to us achieving our goals. And so I really encourage you to fill out that survey. Let us know how you'd like to get involved. And one of us will follow up with you quickly. And I also ask that you follow us on LinkedIn if you are active on LinkedIn. You can find our department's news. The LinkedIn profile is UW-Madison Department of Electrical and Computer Engineering. So I hope to see you there as well. So we've got just a minute left, and I am going to see what the last question was that came in here, and we will address that. So I think this is a good one that came in. Some of our alumni are retired on this town hall, and the question came in, how do we recommend that retired ECE grads who want to read up on some aspects of hardware behind AI, like GPUs, tensor chips, what do you all, our faculty here, faculty panelists, what do you recommend for our retired alumni who want to learn more? TW, Rob, Ramya.
You
Any
can
suggestions
sign
there?
up for my class. No, I think in terms of AI programming, software system, hardware system design, the best learning resources you can find. There are plenty of resources available online. And for example, teaching high performance computing, and it's not just about attending the class. You can also leverage the GPT resources, large language model resources available on the internet or YouTube. There are plenty of them that you can learn how to program AI, TPU, GPU, and all those kind of stuff. And I always told my students, and it's not just about reading the textbook, because in today's AI-driven technology world, it's very fast moving. Learn how to leverage some of these internet resource, large language model, ChatGPT to find a problem and help you solve the problem is also a very important skill set.
Any final thoughts from Rob or Ramya?
Yeah, I was just gonna say ask ChatGPT. No, I'm just kidding. That's sort of what TW said. I don't know I'm not a hardware guy, so I don't know where the best resources would be.
Right. Well, I want to wrap things up here by giving our alumni a huge shout out. Thank you for joining us today. And I also want to applaud our three panelists, TW, Rob, and Ramya. Really grateful for you giving us an hour of your time today to engage with our alumni. We'll look forward to connecting with our alumni next time around. We'll continue this town hall series, and we always welcome the opportunity to engage anytime you're in Madison. Back porch light is always on. Let us know that you're coming into town, and we'll look forward to giving you a VIP tour. And we'll also be in touch if we're in your area over the coming months and year. So take good care, everyone. Thanks again for joining, and on Wisconsin.
Thank you, everyone.
Thank you, everybody.